Hi, my name is Amir. This is Comp 4541. We have a new course code. Last year it was 4901W. This is blockchain, cryptocurrencies, and smart contracts. Now, the thing I have to say at the very beginning of the course is that you can find all the lectures for the previous offerings of this course on YouTube. So this offering is going to go much faster than the previous ones because I'm going to assume you're going to watch those. So, yes, but the first few lectures are pretty much the same. Okay, so this is my name, this is my email address. We have two TAs, both are PhD students doing their PhD in blockchain. And generally feel free to send us emails at any time. So whenever you have any questions, just send an email to me or one of the TAs. Now, I always have to start this course with a disclaimer and say what this course is not about. So this course is not about investment advice. I'm going to give you one piece of investment advice right now, and that's the only one. Never buy any cryptocurrencies. Okay. Now, I work on cryptocurrencies. I do a lot of research here. I never actually buy them. I don't use them for investment. And this is a computer science course, so we are only interested in the technology. And the other thing that this course is not about is anything that has to do with economic predictions. We're going to do some mechanism design and like looking at the incentives of different people, how to cheat in a system or things like that. But I don't care about economy. Again, this is a computer science course. Unfortunately, for many of you, we're not going to do any kind of front-end software development. We're not going to create any software for end users. This is actually quite a theoretical course. We have a lot of coding towards the end of the course. We're going to implement a lot of smart contracts, but usually these contracts just remain at a level that is not really usable for the end users because we are focused on security and proving that the contracts work correctly and things like that. So if you want to do some nice design and create an app, this is not the course for you. And finally, this is something that a lot of students in the previous offerings have mentioned. A lot of the things that you learn in this course can be used for a lot of illegal things. You can do tax evasion or money laundering or anything like that. And we are not condoning that. This is not the reason behind this course. So even if you can do it, please don't. And a very short point about grading. We will have 4 homeworks. Each homework is 10% of your total grade. You actually get to resubmit the homework. So the way it works is that we release the homework, you have a deadline, you have to submit a solution by that deadline. Then you get some feedback from either myself or the TAs, and then you get a new deadline, you get to submit again, and then your score would be the maximum of the 2 attempts. There's also a final project, which is basically implementing a smart contract. That's 30%, and there's going to be a final exam. Okay, so now let me move on to something that actually has to do with cryptocurrencies. This course is going to have 2 parts. In the first part, we're going to just see how a cryptocurrency works. We're basically going to create our own mini version of Bitcoin. And then in the second part, we're going to talk about smart contracts, and especially Ethereum, and we're going to see how to implement smart contracts. So our first goal is to basically design a cryptocurrency. And today I want to just talk about the properties that I like my cryptocurrency to have. And also, I'm old school, so when I say crypto, I mean cryptography. So for your generation, crypto is cryptocurrencies. But whenever I say crypto, it means cryptography. So remember that. Now, this is just my wish list. This is what I wish to achieve. We will achieve some of them, not all of them, by the end of this course. So ideally, I would like to have a currency that is decentralized. I'm sure you've heard that word before. So what do we mean when we say a currency is decentralized? Basically, the most simple definition is that I don't want to have a government or a central bank that controls my currency. Now, why do I care about this? Because imagine that I do have a central bank. The central bank can have all sorts of control over it, right? So even if I'm using cash, let's say I have Hong Kong dollars, the central bank can just print more money, create inflation, and then my money would be worth less than it was before. So I cannot have a central bank or a central government that issues the money. But that's not all the control that they have. Of course, they have all sorts of other mechanisms as well. They get to decide the interest rates. They get to do a lot of things that other people cannot do. So the simplest definition of decentralization is that I don't want to have a government. I don't want to have a central bank. But actually, if I want to go a little bit further, I want to say that my currency is also not controlled by a small group. So you can easily imagine a system where I don't have one central bank, but maybe I have 5 or 10 companies that control everything in the monetary system. And I don't want to have that kind of thing either. So actually, this is the kind of thing that back in 2018 and 2019, Facebook wanted to create. They wanted to create a cryptocurrency that was basically governed by 30 huge American companies. Now, a much better definition for decentralization, and actually the one that I would like the most, is to say that everyone in the system, or in our case on the network, on the internet, has the same access and the same rights. So basically, I want to have a kind of cryptocurrency, a kind of currency in which you can join the currency, you can join the network, and as soon as you join, you can do whatever anyone else can do. There are no roles, there are no special permissions, everyone is equal. Okay? If I can reach that, that's like the holy grail of decentralization, the thing that I would actually love. Now, in a lot of current cryptocurrencies, and especially in Bitcoin, we pretty much achieved the first one. We don't have really governments or central banks in there. But the other two properties are kind of questionable. So we will talk about this later on. For example, in Bitcoin, there is actually a small group of people who control a lot of the hash power and can control the entire system. Now, another issue that we will come back to many times in this course is trustlessness. So this is the assumption that everyone is evil, and if you let someone do an attack, they will do the attack. Okay, so this is an assumption that we're going to have throughout this course. Whenever we're designing anything, we assume that if someone can steal our money, they will do it. Okay, so any protocol that you design has to be trustless. It can never be based on trusting some people, a group of people, one person, whatever. You have to make sure there is no trust. Now, the other thing that I would like to have for my currency is privacy, of course. And this kind of brings us back to cash. So, imagine a world in which there is no credit card and no digital payments. And that was a great world. Everything is just paid by cash. So, before the invention of these modern conveniences, we actually used to have a lot of privacy. So if you're paying by cash, no one can really trace you. If you go to a supermarket, buy something, pay by cash, there is no trace of the transaction, right? I mean, of course, nowadays there are cameras everywhere, so there's that kind of trace, but let's assume the transaction itself has no trace. But then there's also the issue of privacy of the extra information that you have. So if I'm buying, again, let's say something from a supermarket, I don't have to give them my identity, right, if I'm using cash. But as soon as I use a credit card, they're seeing my name on the credit card. So already you see that credit cards actually leak more information than cash. And actually all sorts of current digital payments that we have leak some sort of information. And I want to actually be a little bit more specific about this. So let's say you use a credit card instead of cash. What are the pieces of information that are leaked, in this case, which would not be leaked if I were to just use cash? So I have to look who the information is leaked to. When I'm using my credit card, what are the different parties that are involved there? There's, of course, a merchant that I'm buying from. there are some banks, at least two, my bank and the merchant's bank. And then there is the operator of the network. So if you're using MasterCard or Visa, it's that company, basically. Right. Now, what are the informations that are leaked that normally wouldn't be? So here's the thing. If I were to use cash, the amount of the transaction is something that I would know and the merchant would know. But now my bank also knows the amount. Right? So, and the bank actually can have a record of all of my transactions. So the bank not only knows the amount of my current transaction, it actually knows all of my spending habits. The bank also knows which merchant I bought something from, which is, again, not something that I wish to disclose to the bank. And it also knows the time and place. Now, each one of these pieces of information is actually quite private, and in an ideal world, I wouldn't want to leak any of this information to my bank. Now, why is that? Well, if my bank knows my spending habits, they might be able to use that for advertising. They might be able to use it to, I don't know, decide on the interest rate of the loans that they're going to offer me. They might use it for all sorts of other things. And also they might disclose it to my government, and I don't like that either. And actually, the worst part of it is that I don't trust my bank to be able to keep this data secure. So even if I actually trust my bank and my government, and I love them, and I think that this is a great world, at the end of the day, what if my bank gets hacked? I don't want that information to even exist in the first place. I don't want anyone to be able to access this information. And also, a lot of the information that is disclosed to the bank here is honestly none of the bank's business, right? So, for example, the time and place. Imagine that I'm living in Hong Kong, I have a bank account in Hong Kong, maybe I want to travel internationally, maybe I want to go somewhere else, I don't know. I want to go to Japan and buy something there. Why should my bank know that I'm in Japan? That's just a violation of my privacy that I don't like to happen. Okay. Now, we can look at it from the point of view of the merchant. And this is also catastrophic. So, if you use a credit card, the merchant, of course, sees your card details. And again, in the old days, before the two-step verification and things like that, just having the card details was enough to steal your identity and be able to create transactions on your behalf. That was even worse. And I mean, even nowadays, a lot of credit cards are like that. But basically, the merchant sees your card number, your whatever CVC number, all of those things. It sees your name, because it's written on the card. Again, some banks are getting a little bit better at this and not writing the name. The merchant also knows which bank you're using. And that's also not great. And finally, it sees the type of card that you're using, and based on that, it can make some prediction about like how wealthy you are, probably. Now, this is again bad because the merchant can track you. So if they know your name and card details, even if they don't know your name, if they just know your card details, they can just have a database of all the transactions that have been made with this particular card. And then, again, they can use it for advertising, they can sell the data to others, they can give it to the governments, they can get hacked. So, especially one of the really creepy things is whenever I go on Amazon, Amazon knows exactly what I want. And so this is the kind of thing that is happening. I don't like this. Now, but even worse than both of these cases is the case of the network operator. So let's say you're using a Visa or a MasterCard. These are private companies that are operating these networks, and they see all of the transactions. So they know everything that the bank knows, and they also know everything that the merchant knows. So whatever is leaked to the bank and the merchant is also leaked to the network operator. Now, generally in this course, when we talk about data leaks, we assume that if the data is leaked to one person, it's leaked to everyone. So you either keep it private, or as soon as it's leaked, it's gone forever. So maybe this is not that bad, that they have the exact same information as the bank and the merchant. I mean, given that the bank and the merchant already had this, it was leaked anyway. But the network operators can see an overview of all the transactions. So what this means is that they can actually trace your money. And also, this is, I mean, just in the case of purchases, but if you're just doing transfers of money, then the banks and the governments can trace your money, right? So the idea is that if I pay you and you pay someone else and there are like a sequence of payments, they can figure out where the money came from, where exactly it went, and all of that information. And again, maybe you don't like that. I'm sure you can find all sorts of examples in the news where people had problems because of this, even when they weren't doing illegal things. Anything I say here is a bit political, so I'm just going to say search for Canada. Okay, so as far as we are concerned in this course, what's really important for us is that the transactions should not be connected to your identity. So if I'm making a transaction, that transaction should never leak my identity. If I'm buying something, why should I show an ID to buy it? That's not normal, right? But in the digital world, this has become our new normal. Whenever we're buying something, we are leaking our identity, and we want to avoid that. Now, this would pretty much be solved, at least from the merchant's point of view, if your card just doesn't have your name on it, right? But of course, I don't want my identity to be leaked to the bank and the network operator and the government and the hackers and everyone else as well. But then the other really important issue is that the transactions should not be connected to other transactions. So again, look at this from the merchant's point of view. Even if they don't see your name, if they just see your credit card number, they can just track all the transactions that are made with this particular credit card number. And that's already giving them a really good profile of you and your spending habits and everything, and we don't like that. So these are the things that we have to make sure we achieve. And then there is another thing, which is much less important in this course, because we're people who care about security, and that's convenience. So, and unfortunately, convenience is the reason why a lot of people are using digital banking products and digital payments. Don't do that, use cash. And that's really the thing that I hope you will be convinced of by the end of this course, that you should always use cash. Now, what do we mean by convenience? We want to have online and digital transactions, and ideally I want to be able to transact with anyone, anywhere, even if we are not physically in the same place, so I want this to be global. And I want it to be fast. So the word that we use technically is that I want it to have very little latency, which means that from the time that I create a transaction to the time that the transaction is actually finalized and processed, it shouldn't take long. Now, we will see later on that in Bitcoin, this is actually around 1 hour. But we have much better technologies now. We have much better cryptocurrencies and much faster ones. Now, the other thing that is important for us is to have low transaction fees. Now, it might sound weird to you that we even have transaction fees. But if you think about it, they're unavoidable, right? So if I'm going to have some sort of decentralized system where people join it with their computers from all around the world and do something to keep up the transactions and like everyone's accounts and so on, someone has to pay for it. And if a centralized entity pays for it, then they would own it. So the only way that we can really keep it decentralized is if whenever you want to make a transaction, you pay a transaction fee. But the transaction fees have to be small. Now, many of you are not used to paying transaction fees because a lot of the modern banking products actually hide the transaction fees from the end user. So you're paying it without knowing that you're paying it. So for example, if you consider a credit card, whenever you use a credit card, actually the amount that you're paying is not the same as the amount that is paid to the merchant. The banks and the network operator, and in some cases even the governments, are taking the cut. So there are taxes, there are fees. Usually, if you're using like Visa or MasterCard, it's 2 to 3%. If you're using American Express, it's 6%. And basically, what's happening with the credit cards is that they have contracts with the merchants that say when someone uses our credit card, you cannot charge a higher amount. So the transaction fee is already included in the price. And it's even included in the price for the people who are not using the credit cards, which is awful. But anyway, we want to have low transaction fees. And also, by the way, the same thing happens with the banks. So if you have a bank account, especially in Hong Kong, and if you're making transactions like using FPS and it's free, it's actually not free because they're paying you very little interest for keeping your money, and that's how they have the transaction fees. Okay. But another important thing, and this is something that people don't think about when we talk about the currency usually, but it's actually going to be the main focus of this course, is that we don't just spend money, we don't just buy stuff with money, we also write contracts with money. And contracting is a very important aspect of a currency. So if you have any kind of currency, it's meaningless if you cannot really write a contract with it. I want to be able to have loans, I want to be able to have mortgages, I want to be able to have all sorts of contracts. I don't know, CFDs, whatever. Now, the problem is that if I have a contract, I also need an enforcer for that contract. Who's going to enforce it? So suppose that I write a contract with you, maybe I bet with you about something, about some game in sports, whatever, who wins. And then I say, if this team won, I'm going to pay you $50. If that team won, you have to pay me $50. And let's say we write down this contract and sign it. Now, in the real world, this is enforceable in the sense that if the contract requires you to pay me and you don't pay me, I can go to court, sue you, and then they have the power to enforce it. Now, the problem here is actually two separate problems. Well, one problem is centralization. Like, the whole point of creating a cryptocurrency was that we didn't want to have central government and central banks, so courts are also the same. Like, a judge is a centralized entity, and I don't want anyone to have centralized power over us. So I cannot write a contract and just hope that a judge will enforce it or the justice system will enforce it. That's not a thing for us. And also the other problem is we said we want our currency to be global. So what if we're just in different countries and there is no one court that has jurisdiction over both of us? So how can we write contracts in those cases? So this is another issue which will eventually kind of be solved with smart contracts, but you will see that it opens a very weird can of worms, and then we will have to spend half of this course just talking about the security of smart contracts. Okay. So moving on, I hope that you're now convinced to use cash, and you're also convinced that this is going to be an interesting course. We're trying to mimic cash as much as possible, and by the end of the course we will even find some security properties that are even stronger than cash. But for now, I have to tell you that the course is going to start with a lot of cryptography, because of course that's what we use to create cryptocurrencies. So we're going to start with cryptographic primitives. We're going to spend basically 4 or 5 lectures on these and see how each one of them work. And then at some point we're going to merge all of them together to create a cryptocurrency. So in the first few sessions of the course, you're going to see a bunch of things that might seem very unrelated to each other and very unrelated to money. But then at some point there is a lecture that puts all of them together and creates Bitcoin. Okay? So the first question that we will look into, well, actually, no, this is not the first question that I will look into, but okay, one of the questions that we will look into is the question of secure communication. So let's say that I have an unsecure channel. For example, I have the internet and I want to send you some message. Now my problem is that other people can actually see the communication between us. So again, my internet service provider, my government, your government, whatever, whoever owns the cables under the sea, they can all see the data that is going through them. So I want to make sure that when I send you a message, only you can read it. And of course, the solution to this is to use cryptography and to first encrypt the message. So I have to encrypt it in a way that makes sure only you can decrypt it, the intended recipient can decrypt it, and then I send it to you and you will decrypt it. Now, this is like a huge part of this course. We will talk about how to create encryption and decryption mechanisms. Now, another issue is that maybe someone is trying to fake a message. Maybe I didn't send you a message, but my ISP or my government or a hacker, for us all of these are the same, they're trying to send a message to you and fake it and say that I was actually the one who sent this message. Right? So how can you verify that a message was actually issued by a specific user? And here we will have the concept of digital signatures, which are very different from real-world signatures. And we will see how you can sign a message so that anyone who sees the signature can verify that it was actually created by you and no one else. Now, the other central thing that we will see is basically how to commit to something, how to make sure that, let's say, if I have a history, and this can be a history of anything, in our case, of course, it's a history of transactions, how can I make sure that the history cannot be changed? How can I make sure that no one can change what has happened in the past? Because, again, at the end of the day, if I have a cryptocurrency, I have a bunch of different players on the network. These are the nodes that are keeping track of everything. Maybe someone wants to cheat. Maybe someone wants to change the history of the network. And I want to make sure that that cannot happen. And one of the primitives that we use here is a cryptographic hash function. And this is actually something that hopefully I will get into today. And then finally, probably the most important problem that we will talk about in this course is consensus. So how do we reach consensus about the ownership of the funds? Like, how do we make sure that everyone on the network agrees about who owns this particular coin? Because you see, if you have a centralized system, that's not hard. If you have a bank, you own your money if the bank says you own it. Right? You own your money if you own it in the database that is stored on the bank's servers. But what happens if I have a decentralized system? What happens if I have tens of thousands of nodes, tens of thousands of computers on a network, and no one has any kind of advantage or privilege over anyone else? So when do I actually own some money? What if half of the people on the network believe that I own it and the other half believe that someone else owns this piece of money? Like, I have to sort this out. I have to make sure that we reach a consensus and everyone is on the same page. And for this, actually, we will see several different protocols in this course. The two most important ones are proof of work and proof of stake. Okay. We basically have only 20 minutes now, but I'm going to start the theory finally. Okay, so we're going to start with our first definition. And okay, so the first part of the course is quite theoretical and it has a lot of mathematics, but as long as you understand the intuitions here, you'll be fine. And in the second part, you can just do coding mainly. Okay. So we're going to talk about hash functions and especially cryptographic hash functions. So first, I'm going to give you the definition of a hash function. A hash function is basically a function, let's call it h, that takes a string, and the string that it takes can be of any length. So I use sigma star to denote the set of strings of any length. And then no matter what the length of the input was, it's always going to give you an output of a fixed length. Now, let's say 256. Okay? So it gets an input. The input can be long or short or anything. Imagine that the input is just a sequence of zeros and ones. And it always gives you exactly 256 bits in the output. Now, instead of this 256, of course, you can have hash functions that have other sizes, 1024, whatever. But we generally use 256. So instead of 256, I'm just going to write it. So that's just the definition of a hash function. So very simple. The input is going to be a string, and it can have any length. The output is always a string of a fixed length. And also, you don't need to write anything because I write everything for you, and I also record everything and put it on YouTube. So, pretty easy course. Okay. Right. So this is what we call a hash function. But in order for it to be a cryptographic hash function, it has to satisfy some extra requirements. Now, here are the requirements. The first one is called collision resistance. Basically, what this means is that no one can find two different values that have the same hash. Okay? So, this definition is that we cannot find two different values, let's say x and y, that are not the same, such that the hash of x is equal to the hash of y. Now, very importantly, I'm not saying that these kinds of values don't exist. I'm just saying we can't find them. And in this course, these two things are different. Because if I say that there are no two different values that have the same hash, that's basically saying that the hash function is one-to-one. And that's impossible. Because if you look at my hash function, it's mapping the set of all strings to set of strings of length n. And on this side, I have an infinite set, right? Whereas this one is a finite set. It actually has 2 to the power of n elements, if I have strings of zeros and ones of length n, right? So mathematically, we know that it's impossible to have a one-to-one function from an infinite set to a finite set. So mathematically speaking, there are values, there are different strings that have the same hash. But I'm saying we can't find them. And we can't find them means that no one knows any algorithm that can find these kinds of values, let's say, in the lifetime of the universe. Okay? So I have to maybe define this, which is no one knows an algorithm that finds such a thing, let's say, in 10 to the power of 30 years, or something like that. Okay? Now, this is a much weaker guarantee than the mathematical guarantee of one-to-oneness. And also, another point here which I have to mention is that I'm not saying there is no algorithm that can find this. I'm just saying no one knows an algorithm that can find this. So this is a part of cryptography where we are not really on firm ground. It's like we have some hash functions. In practice, we don't know how to break them. We don't know how to find collisions in them. But we also don't have any proof that no one can find the collision. Maybe someone can find the collision. It's just that people haven't been smart enough until now to do it. Okay. But for all practical purposes, this means that if I give you the hash of a number, I cannot change that number later on to something else that has the same hash. For all practical purposes. Okay. The second property is the hiding property, which basically says that you cannot invert a hash function. So if I give you the hash value, you cannot find the pre-image of the hash. So it's like this. Given some y, which is of length n, we cannot find some string x, which can be of any length, such that the hash of x is equal to y. Okay? So if I give you the output of the hash function, you cannot find its input. And actually, it's even more than this. ideally, and this is very idealistic, we don't actually reach this, I want to say that you cannot find any information about X. Not only you cannot find X itself, you cannot know anything about X. You cannot know whether X is odd or even, right? So this is a little bit stronger than saying that you cannot find the value of X exactly. You cannot find any information about it. But for now, we don't really care about that. We will come back to this when we talk about zero-knowledge proofs. There we will see towards the end of the course that having no information about something is actually very important. And finally, there is another property called puzzle friendliness. We will come back to this when we talk about proof of work. So for now, just know that this exists, but I'm going to skip over it. So for the purpose of this lecture, a cryptographic hash function is just a function that maps any string to strings of a fixed length, and also it's collision resistant and hiding. Now let's see what we can do with it. Here's the first application that I want to show you. Let's say that I have a database of files, and let's say that my files are huge and my database is also huge. So this is my problem. I have a large database, let's call it big F, of large files. Okay? Let's imagine that each one of my files is several gigabytes, and maybe I have, I don't know, millions or billions of files. Okay? Now, someone gives me a new file, and the question is this file already in my database or not? So, given a file, let's call it F, decide whether F is already in your database. Okay. Now, this is the kind of problem that you would have if you have, for example, a torrent service. Right? So you have different people who have stored different files, and someone is asking for a particular file. You want to know if you have the file in there. Or maybe someone is providing this file, let's say, I don't know, your Google Drive, someone is uploading a new file. If it's the same as one of the files that you already have, you don't want to store it again. You just want to remember that this is the same file and just keep a pointer. Right? So how do we solve this? Well, we can just use a hash function. It's very simple. Whenever I add a file to my database, I also compute the hash of the file. And I just keep a set of all the hashes. And when a new file comes in, I compute the hash and I ask, does this hash already exist? And if it does, I say, okay, I already have this file. Otherwise, I just add the file. So the solution is very simple. Store hashes of files. And it's up to you what kind of data structure you want to use for this. You can just use a set, a binary search tree. You can use whatever you want. Just use a database that can let you search for hashes really fast. So personally, I would use like a balanced binary search tree, and then I can find the hashes in logarithmic time. So store the hashes of files, and then just search for the hash of this new file whenever you need it. Okay. Now, how much time are we spending here? You see, hopefully, I have a hash function that is computable in linear time. And this is actually the case for the real-world hash functions that we use. Like in Bitcoin, we're going to use a hash function called SHA-256. You can actually search for this. This is a very complicated function. I don't want to get into how you make hash functions because we will never make our own hash function. We will just use the hash functions that already exist. But yeah, these hash functions, they generally have a runtime that is like O size of the input, so they are linear. Okay? So in general, if I have something like this, every time that I get a new file, I have to just process the file once, find its hash, and that's it. The next time, I don't have to go over this file again. Whereas if I didn't have the hashes, it would be a nightmare, right? Whenever I got a new file, I had to go back and compare this file bit by bit with every one of the previous files. And that could be catastrophic for me. It could take a lot of time. But just storing the hashes is going to be super fast. Okay. Now, why does this work? Like, which property of the hash function are we using here? We are using the collision resistance, right? So the idea is that if I have two files that are the same, if I have file 1, and by the way, when I say file or string, these two things are the same for me, because a file is a sequence of zeros and ones, a string is also a sequence of zeros and ones. So my analysis is that if I have two different files, let's say, it's really hard to write here. If I have two equal files, if f1 is equal to f2, of course the hash of f1 is also equal to hash of f2, because that's just the definition of what a function is. It's a function, so the hash of f1 is equal to the hash of f2. Now, if I have two files that are not the same, technically, again, mathematically speaking, their hashes can be the same, right? But in practice, if that happens, it means that I have broken the hash function. It means that I found a collision in the hash function, and I'm assuming that's impossible, right? So if f1 is not equal to f2, but hash of f1 is equal to the hash of f2, this violates collision resistance. Because now I was able, through some algorithm, I don't know whatever algorithm it was that created these files and gave them to me, I've been able to find a collision in the hash function. And because we think this is impossible, at least for the hash functions that we're using, we hope that this would never happen in practice. Okay. Now, another application which we don't have enough time to cover entirely, but we will cover in the next session, is to create a ledger or a history of transactions that cannot be changed. Now, maybe I can just give you some intuition, but I'm not going to go into this in this session. So here, when I was searching for files using their hashes, the idea was that I want to use the hash as some sort of a digest, as a summary of the whole file. And this is the kind of summary that changes if the file changes. Okay, so this is like using hash as a digest. But there is another way of looking at hashes, and the idea there is that I can see a hash as a pointer. So let's say I have a data structure. Let's say I have a linked list or a binary search tree or any other data structure that you've seen in your algorithms or data structures courses. Now you can have different objects, and you can have objects that point to other objects. Right? So for example, if I have a tree, I would say that every node in my tree points to its children. Right? This is a binary tree, let's say, and every node is pointing to its children. Now, how do these pointers work in programming languages like C or C++? Basically, the idea is that each one of these items is saved somewhere in your memory, somewhere on your RAM, and that location has a number, and the pointer is basically the number. It's basically telling you, so whenever I'm writing this pointer here, this pointer is basically the location in memory. So if X is pointing to Y, what X actually knows is where have I stored Y in my memory. Now there is a problem with this kind of pointer, and the problem is that if I change Y, X has no way of knowing that Y has changed. Right? So And I mean, that's desirable in a lot of situations, but not for us. So basically, all X knows is that the information about Y can be found in this particular location. So if that location changes, X just accepts the new value of Y, right? But instead of doing this, instead of saving the location in memory, what we can do is save the hash of Y. Okay? So let's say that when X wants to have a pointer to Y, instead of the location, the pointer itself is literally the hash of Y. Now, what happens if I do this? If I do this, it's much harder to locate Y. Because all X knows is that I have, let's say, a left child, and my left child has this particular hash value. It doesn't know where the left child is. So if you want to walk over this data structure and go from X to Y, you have to have some extra data structure that actually lets you search by hash. So it makes life harder. But it gives you immutability in the sense that if someone changes the value of Y, that also changes the hash of Y, which means that X is no longer pointing to Y. X is pointing only to the previous original value of the Y. So whenever you change the value that is being pointed to, all of the pointers are now invalid, and they're no longer pointing to the same thing. Now, this is a property that we will use in the next session. Okay, thanks. So see you soon.